So, my name is Emily Petroff, and I was asked to moderate a discussion with many of our speakers from this morning, all of whom are in some way related to observing with telescopes, on the sort of broad topic of observations. Uh, so, I wanted to start off with just a few slides about what we talk about when we're talking about observations that we make with radio telescopes, since I know there are theorists, non-radio observers in the room, and I think it's kind of useful to go through what we actually measure with a radio telescope just so we're all on the same page. Okay, so this is kind of important. As observers, what are we actually capable of measuring? There's a lot of things, but they are somewhat limited, right? So um, when we observe an FRB, we're able to measure, at what radio frequency it was discovered. Sometimes you can observe with multiple telescopes and observe at different wavelengths and see if you see an FRB at different wavelengths at the same time. We can measure the pulse duration and in some cases subpulse structure. We'll get to that in a little bit. We can measure the sky location, dispersion measure, which then from that we can maybe infer an upper limit on the distance to the source. Things like scattering, spectral features that we've heard about this morning already from Vicky and other people. We really only measure signal to noise ratio. We don't measure flux or fluence directly, right? So unless we're able to flux calibrate our instruments precisely, but in most cases with FRBs, we get a signal to noise ratio, and then from that we infer things like flux and fluence and energy. We can, in some cases, measure linear and circular polarization and positioning, polarization angle, sometimes rotation measure. If we're lucky, we can find repetition, and then we can get these all-sky rates above a certain fluence. And then we can measure things like upper limits on detection at a certain frequency or something like that. We can get upper limits on a lot of these properties, actually. Okay, so this is basically, these are the things that we measure with the telescopes. We have some different observing strategies when it comes to finding FRBs with our radio telescope. So the first slide kind of dealt with individual FRBs. But then when we're actually targeting FRBs with a telescope, in some cases we can get distributions in a large sample, like the DM distribution that Vicky showed us in her talk. We can, with a large sample, get things like a fluence distribution or a width distribution of FRBs, all sky distribution. We've seen some of these plots already today. And then for specific FRBs that we're able to localize, these are sort of two separate strategies, right? The sort of big population strategy and the localized individual individual FRBs and do precise things with one specific burst. For these specifically localized ones, we can actually get things like the host galaxy type, if there's persistent emission, star formation rate of the host, and the host DM environment maybe. But it's worth mentioning that we can't get this for all FRBs at the moment, and nor will we likely be able to get that for all FRBs in the future. And then if we have voltages available from our telescope, we can sometimes get this microstructure. We can see these microsecond bursts, or potentially we could get better resolution than that. But I will note that all of these things are extremely biased by our observing setup. So there are some things that maybe, I think this is what I really wanted to make clear before we start the discussion, is that we don't measure all things equally for all FRBs, and not all telescopes measure all things equally. And so things like the time and frequency resolution of our instrument and how we channelize, or if we're able to get voltages that we can analyze offline, heavily influences the type of information that we can determine for each individual burst. Our observing time on sky, our observing cadence, our choice of observing field, like Casey mentioned, sometimes we don't have control over where we're pointing. We just we're tagging along for the observations with other people. Things like field of view and the beam size and the resolution that we have on the sky are very important. Some FRBs, we can't localize them very well. Some of them we can do extremely well with the voltages, or with ASCAP offline, you can do a nice localization. And then also we can't get polarization for all of them. So, we've mentioned that, 11, and Vicky mentioned that like 11 FRBs have measured polarization. That doesn't mean, or that they have linear polarization. That doesn't mean that other FRBs have not been seen to be polarized. It's just that we don't have the polarization data for those FRBs, right? So we're limited there. Our telescope sensitivity, and then this is a really big one that's going to become much bigger in the future, is the RFI environment of our telescopes also heavily influences what we see and how we see it. So is kind of visually demonstrated by this really nice plot from Well Farah's paper a few years ago for 170827, as burst from a long glow, where this is the incoherent pulse itself. So you can see it just looks kind of like a Gaussian or a single peak pulse. But then they preserve the voltage data, and then when you go back and look at it, it has this superb microsecond structure and frequency time structure that you can see in the pulse itself. So it's these are the same burst, but just totally depends on the way that you're taking your data, what sort of information you can actually extract from an individual FRB. So that being said, I wanted to kind of set the stage for our panel, but to kick off our discussion, I've kind of asked our panelists to chime in on a few of these topics. And so, I mean, we can go question by question, I suppose, but these are the main things that I think we might want to discuss just to kick off this hour. So this is a question to our panelists. There's many of you, so this could take a while. So what, if any, new observations do you think would be transformational to our understanding of FRBs? What do you think is the most constraining observational measurement we've made so far on an individual or a population, whatever? And then what properties do you feel are most useful for theorists? What do you think are the sort of the things that can constrain future theoretical work? So with that, I'm going to come around this side and look at our panel. And would any of you like to kick us off with any of these? All right, well then I'm just going to call on Matthew, because you haven't talked yet today.
The release of the chime results for number one. I think like fast detecting one at z equals 6 or something would be pretty transformational. Mm-hmm. I'm very curious to know whether something about either the maximum frequency that an FRB can be emitted at or the scattering mean, can we actually see them at z equals 6 even if you have fast? I'm not sure if we have any fast people here, but it's a bit of a shame. But I know that they hammered the repeater at one point and got lots and lots of bursts. I believe there's no periodicity. I think a periodicity of 16 days is really, really interesting, but a periodicity of like 6 milliseconds would also be really, really interesting. So I think, that's kind of where I'm thinking about transformational things. If you look at how much money we're going to spend on the SKA and how much money we spent on Chime, I think that there's an interesting case for a dedicated Chime-like facility, maybe slightly higher frequency, maybe a sort of an international project or something at a radio quiet site that could be detecting these things many times a day, but also doing things like pulsar timing. Like, I haven't heard anything yet about the pulsar timing out of Chime, but I know that they're looking at hundreds. I mean, we look at 400 with Molonglo, and it's got crap sensitivity. So things like a dedicated cylinder-y pulsar timing FRB thing is interesting because there's no moving parts on these telescopes, which makes them a lot cheaper to run than ones that do move. I've probably spoken enough about bullet point number one.
No moving parts, I guess. I thought you just invented DSA 2000 there. Sort of meets your spec of a dedicated telescope that is low cost, but will do lots of FRB localization and pulsar timing.
Right. Ryan, did you have something?
But shouldn't it be in the southern hemisphere to match up with LSST? Don't you need LSST to get your photometric redshifts?
There's more galaxy in the southern hemisphere.
Well, that's also good for pulsar searching, too.
Okay.
So for the first point, I think I'll agree with Matthew on one of them, but on the other one, I'll suggest instead of a high redshift z equals 6 FRB, something like z equals like next door would be a really, really interesting FRB to find, because that gives us a lot more possibility of digging into the host properties and possibly even identifying the specific source it's coming from. So very bright, very nearby FRBs somehow. I mean, finding one at z equals 6 would be great in terms of, yes, can be done, and the cosmologist will be happy with that, I guess. But in terms of finding out what it is, closer ones may be better.
We had a comment. Can you use your microphone? Yeah.
Is there a systematic way to find the nearest FRB? Is there like going on at chime or?
Yes,
Stare.
definitely. Yes, yeah, I'll take that because because we have. I mean, it depends on whether you think there is a cutoff to the luminosity function or not at the low end. If you make some modest extrapolations, but of order, roughly an order of magnitude down, then certainly just make your antenna smaller and smaller and smaller. You see a larger field of view, and eventually you should be sensitive still to the nearest events. And so we have this project called STARE at the moment, where the paper just came out, I think. It was in the archive a few weeks ago, maybe a month ago or so. And yeah, we've got a array of 3 DSA 10 feeds pointing up with the same receivers and everything, but they're spread by several hundred kilometers around the southwest US. And the idea is that anti-coincidence filtering can get rid of RFI, and anything that's coincident in the sites is real. And there's enough localization with this thing, just with the time of flight, to get you to any nearby galaxies. And so I certainly would agree with you, Shami and Wenbin, that I think there's a lot that can be done with very local events.
Be that this depends on the intrinsic luminosity function of FRBs, and it may be that if it's sufficiently flat, the brightest things are actually farthest away.
Agreed. Yeah. Brightest, most luminous.
Most luminous, sorry. Oh, sorry, the brightest that you see are actually the farthest away if the luminosity function is sufficiently flat.
Yep.
So if we're thinking about new observations, then the first thing that comes to my mind is that I think if we think ahead to an era of thousands or tens of thousands of FRBs, that propagation effects are really underexplored. Like, what will we do when we start finding gravitationally lensed FRBs? How can FRBs inform us about the IGM? Like, you can do things like by cross-correlating foreground galaxies with DMs or scattering properties of background FRBs, you can answer questions like, how are the electrons distributed around galaxy clusters? Which is a question that's very, very difficult to answer with other cosmological observations.
Did I get it?
Do you have a comment specifically on that? Yeah. Okay, yeah.
About this propagation effects, about this dispersion measure thing. Because recently I've read a paper by Matsutaka Fukuhita about how baryons are distributed in the intergalactic medium. And at least according to that paper, it's highly non-trivial. We should not think about baryon density between galaxies. There is no such thing according to this paper by Fukuhita. They are not even distributed according to an FW either. There are some very funny tails and whatever. So it looks like, and we have seen this beautiful linear, quasi-linear, whatever, correlation with redshift in a couple of talks today. So it looks like you people are already in a position to make some highly non-trivial statements about relevant for cosmology, because looks like you are quickly accumulating the necessary statistics here. Just a brief comment.
Vicky, go ahead.
Just 2 points. One, to come back to the low DM FRBs, that if you look in the among the published chime repeaters, there's quite a few actually already that are very low dispersion measure, including the one that was, well, so it depends. And so distance of 150 megaparsecs, maybe that's not close enough for you, but there's others that source has a dispersion measure excess of I think 150, whereas there's others already in the repeater sample. So if you want to that have lower XSDM, significantly lower. So I would say a systematic way would be to get people should be watching those with interferometers to localize them, because I think those are already in the literature good bets for nearby FRBs.
Did chime
Yeah. So this is actually really interesting. So we use the models for the galactic content, the NE 2001 and the YMW16 models for, and then we use some statistical guess to say, okay, is this extragalactic? We actually have three classes. We have galactic, ambiguous, and extragalactic. And then so ambiguous, we'll keep everything, and we look at them, and then you puzzle sometimes, and you say, is this maybe it's in the galaxy? How would you know? You'd call it a rat if it was in the galaxy, and so you say, okay, proper motion? No, that's not gonna, how are you ever gonna do this? And then you say, okay, if you could localize it, and there's nothing there, then that's in the halo. Or now I hear they see some have nothing, and then you say it's a dwarf. But I see Chris wants to say something, so I'll stop.
And then we'll go to you after that. Yeah, Chris.
What's the brightest galactic burst CHIME has seen? Can you say? Galactic. Yes. I mean, if we're sampling,
we see many crab giant.
Yes, but
giant pulses from the crab.
I mean, the question's obvious, right? If you're sampling the tail of the giant pulse distribution at cosmological distances, you're also sampling the lower part of the distribution within the galaxy more efficiently than has ever been done before. Are the two distributions meeting up?
No. There's a big gap there.
Galactic and the faintest extragalactic.
Yeah, I say
I don't think they do.
Crab GPs way underestimate.
Well, but my question was more, just take what you're observing in the Milky Way and connect it up with what you're observing in the extragalactic universe.
So the crab energy distribution is pretty well characterized for a long time, and I think Jim has a couple of papers on Mora on how to infer that.
In principle, there could be other sources.
But, yeah.
But that's something we could look at. We haven't explicitly done that analysis.
But I think it's a really interesting point, though, also to not even do this between the galactic and the extragalactic case, but just look as a function of dn.
Mm-hmm.
How many fewer do you see as you go to higher and higher dns? Because even that starts to tell you something about your how far down the luminosity function extends, right? And I think, yeah.
So. We had one event. We were looking 70 degrees away from the crab pulsar with Molonglo, and we saw an FRB from it. And we thought, gee, that's amazing. It's got the same DM as the crab, but we were pointing 70 degrees away. So it's amazing what you can find in a side lobe.
That's familiar with that phenomenon.
Could I ask one more question? Or?
Yeah, very quickly, yeah.
Okay. How much coordination is there with CMB experiments? For example, CLASS, Bennett's experiment, has been surveying the sky at 40 gigahertz for years. They see a big chunk of the sky every day at 40 gigahertz.
But with what time resolution?
Oh, I don't think very good, but if you.
I think there is a published South Pole telescope has a transient which one integration long. They don't know how to infer it. They think it might be a GRB or potentially, but there are things like that happen.
So they often scan and so often record with sub-second timescales. I know that people are searching. A big issue is that they're often done with bolometers, and so you get one channel, and so.
Yeah. Okay, sorry. Roger's had his hand up for a long time.
If I take your first question literally, I would have thought the answer was to see a gravitational wave or a VHA neutrino coincident temporally. I mean, that would be, I think, the most transformational discovery. And not seeing them, of course, is also prescriptive. I mean, it would, if you find one, it rules out large swaths of possibilities. And if you don't continue not to find them, then I think that perhaps does the same as well. And to me, that's probably the most prescriptive, and it probably wouldn't be bad for funding either. But those, these techniques are getting much more sensitive with time, just like you are. So, it's worth really plugging away with that and advertising that you're plugging away with that.
Just a question. So, to what distance would you? I mean, you're talking about events within some volume that you could detect what you said. So what distance?
I wouldn't make any hypotheses. It's so easy. I mean, it's not a hard thing to just look for temporal coincidences. Just like Chris said with the,
you know, the big radio surveys, the resolution is obviously not so good there, but just doing it, you know, without overthinking the problem.
Yeah, LIGO's out.
Yeah, and it's getting
if
better.
it's optimally aligned,
it's getting better.
There's one that's localized to 150 megaparsecs, so there's one.
don't overthink it. Just do it.
Yeah, it was 40 megaparsecs.
Yeah.
Oh yes. Oh, sorry. Yes, Riharsh.
Chris's question about the CMB telescopes. So they do sample at extremely high rates, but the reason they do it is because they get cosmic ray hits on the bolometers, and they can't distinguish between cosmic ray hits, and it's really hard, rather it's not impossible to distinguish between the cosmic ray hits and FRBs. So if they had two bolometers looking at the same patch of the sky at the same time, and you get a coincident hit, that would be an FRB. But with a single pixel on each location, it's really hard. But yeah, people have tried, as Casey mentioned, the SPT has looked at this a little bit.
There was one of you about to.
Make a quick. I was going to get into your second point actually, because if I would think about what has really constrained the field so far, I mean, the obvious one is the time resolution, right? In their millisecond burst, but really, when you look at it, they can go from a few microseconds all the way up to tens of milliseconds, right? And then, of course, the next thing you go is the energy, right? Once you have some localizations, you've got a sense of the energy scale, but I guess if I go beyond those two, I find it hard to think of what else we've actually constrained.
Yeah.
And I know that, Liam, you've thought a lot about this as well, but it's kind of hard to think about where we're actually constrained in the population besides roughly those two quantities.
Laura.
So for me, I think one of the most constraining observations we've made is polarization. So the very high linear polarization, and specifically this flat position angle, because we know it has to be coherent emission. Therefore, almost certainly strong magnetic fields are involved, and those are the properties which are telling us something about the geometry of those magnetic fields. And so I think that among the two you mentioned is also very constraining from the emission mechanism point of view.
Is the flat PA known in 3 or 4 FRBs, right?
Well, it seems, I'm doing this from the top of my head. I think the ones where you have very high time resolution, where you actually have many points across the profile, if I remember correctly, show flat. I mean, this ASCAP one is new. Of course, that's different. But I believe most of them have been flat.
Yeah, Manisha, and Daniela also, you can chime in on this, but let's get Manisha.
Mm-hmm. Yeah, but arguably, yeah. I mean, it's true. There's just a few points across that. That's why I say very well resolved.
I mean, yeah, it has to be temporally resolved, and it can't be scattering either, right? So if you scatter broaden it, it will still stay flat, I think, or could potentially still stay flat, right? So
unless you have ridiculously different magnetic fields in different regions in different
but I mean, flat PAs is not. You know, you have to be careful when you interpret those for many of the pulses.
Oh, and I just wanted to add that I can think of lots of radio pulsars where it's totally flat position angles, but
yeah.
So the other constraining thing I was mentioning was strict periodicity. If you could identify that there was an underlying strict periodicity in the FRBs, then you could say, I mean, it would somewhat conclusively argue for something which was not a stochastic mechanism for the production.
Yeah.
Well, if you'd asked me that question too before last week, I would have said periodicity would be the thing that would break this open. And yet we're here still sort of throwing our hands up like, it could be this event. Burst. I got you. Okay.
Right.
But even then, that one is pretty definitive what's happening. But I do feel like this 16-day period would have gotten us closer to answering simple things about is the emission mechanism dominated by the source, or is it a propagation effect that's really contributing to the luminosities we see? And we don't have an obvious answer to that yet. I'm surprised. I feel like we would have gotten that out of a 16-day period somehow.
That's fair.
So intrinsic versus extrinsic for me is like the number one question that we haven't answered, despite all the amazing breakthroughs of the last year.
Okay, so Bing and then Eli.
Fashion. Sorry.
So first, I want to echo what Roger said. I just searched for some information regarding the gravitational wave association. So we looked into that. If we look at the DM less than 100 FRBs, once we collect, say, 100 of them without any association, that rule out 10% of the FRBs are associated with double neutron star mergers. If we got 1,000, then that rule out to like 1% FRBs are associated neutron. So there's a paper on that, just to work out the absolute numbers. But in terms of these most constraining properties, as a theorist, I think so. Some of the properties, they are more like footprints, fingerprints, but some of them are really smoking guns. And smoking guns, of course, gravitational wave association is important. The periodicity is very important. Even the binary periodicity, I think, is already very important. One related question to the earlier discussion is actually the difference between rats and FRBs. If we get CN, these two populations very nearby, and how do we tell which is which? So the question is, do all rats have the strict periodicity and FRBs don't? Is that one criteria, or?
Yeah, where do you want to jump?
A word about the rats. I mean, on the one hand, there are a couple rats, like galactic neutron stars, that we can't detect a periodicity for. They're very rare, but there's a few of them that we have many, many pulses and can't calculate a period. And I'm imagining that's due to like very broad multi-component profiles, and you get different pulses from different components every time and kind of separated by large windows. So I think those kind of comparisons are interesting. At the same time, the amplitudes of the pulses from all of these galactic rats are not any higher than normal pulsar pulses. I mean, there's no evidence that they're brighter. And so I think you just can't really, I mean, they're so different from FRBs in that respect that it's really hard to talk about like a common emission mechanism just based on the amplitudes. And we do have some kind of FRB rats where only one pulse has been detected, and they're galactic objects. We've only detected one, and it looks definitely real, and there's been lots of re-observations. So they're analogs to FRBs in that way. But again, they're just much, much fainter. They're just like normal pulsar brightnesses.
And just to ask, also spectrally, so the 121102 has these wonky spectra, which you never see in, or
Yeah.
I don't want to say never, but do we ever?
Yeah, thanks for, So a student, a grad student at WVU and I wrote a paper like a year ago, Shapiro, Albert et al., and we looked at all the rat data we had, and we made single pulse spectral plots, just like the ones for the FRBs, and we were super hopeful that we would find that some of them also showed this very wonky spectra, and they're all totally boring. I mean, they all just look really boring. There's evidence for scintillation, diffractive scintillation, but that's about it. There's absolutely no evidence for any interesting modulation or set trombone-ish features. So yeah.
Okay, so Danielle, did you want to say something about that? Okay, great. So can we move on to Ellie's point? Can you use your microphone as well? Sorry, I'm supposed to remind people to use the microphone.
It's quite likely that the energy that is emitted in the radio is some relatively small fraction of the total energy that is emitted in these bursts. And I mean, in the popular models that are discussed, it could be 6 orders of magnitude difference or even more. So 10 to the 46 ergs emission in optical X-ray gamma rays should possibly be detectable. And so I think that follow-ups of well-localized events for deep exposures or a shallower, very wide field of view observations in optical X-rays, gamma rays could be very, I mean, they could provide a very significant hint to the events if something is detected.
Yeah.
And also if nothing is detected, it's also a good, it's going to be a strong constraint.
Yeah.
And so 10 to the 46 ergs per second could be seen very far away.
Paul.
So,
yeah, I definitely agree. And yeah, we have to target the nearby sources because those are the ones where we can get down to things like 10 to the 46 ergs. We tried this with FRB 121102, and we weren't quite getting down to that level. So it's something we have to chip away at. Yeah.
You had a comment back there.
Has there been any evidence for subburst periodicities in the burst light curves, and can current observation facilities detect them?
Subburst periodicities. So like,
just take the light curve and look at the periodogram of it.
I can. I'm on a paper that claims tentative evidence of one. I won't say any more.
Any frequencies?
This was the R2, I think, where one of the bursts, I think, there were 5 of them all spaced by 13 milliseconds, which was very interesting to a theory colleague of mine, which motivated a study, which actually eventually didn't depend on that. But, yeah.
Okay, Jim, you've had your hand up for a while.
Okay, I think for number one there, observations that constrain the age of the source are highly interesting. So I think an association with a GRB or a gravitational wave source is one thing, but really we have to find more persistent sources, because I think it's the theory that has given the constrained age for FRB 121102. So it'd be nice to see a sequence. So let's get to work.
Do you have a comment on that, Brian?
I had a slightly different thing, so if you want to say something.
Okay, yeah. So.
Okay, all right. Well, I was going to ask. I mean, I'm surprised the issue hasn't come up, but like, are there repeaters and non-repeaters? And like, so we saw these observational evidence that maybe the non-repeaters are shorter, and I've heard conflicting things as to there could be observational effects that lead to this. And I was interested in the panel's thoughts on this. Do we have evidence that these are distinct properties? How are we going to test the hypothesis that? I mean, obviously, you can't wait forever to see if something is going to repeat, but can we? How do we test the hypothesis there's a continuum of properties? I guess is the question.
Mm-hmm. Who wants to talk first? Paul, why don't
So
you?
I'd say that with CHIME, we're applying, the same selection to the repeaters and the non-repeaters, and seeing that they're wider. But that doesn't necessarily mean there's 2 separate sources there. It could just be that the apparent width is related to more frequent repeating, right?
Right. I mean, you could imagine a correlation like that. I guess I'm wondering, are there maybe Xiaomi wants to come? No, you don't. Okay. I've heard skepticism about the reality of this, but okay.
No, I think what Paul said is right, that the repeat things that are easier to detect repetitions from might turn out to be broader pulses for some reason. I mean, there could be selection effects like that. And I have this complicated, possibly related to the distance as well, because the repeater redshifts so far are closer than the non-as-yet detected repeat distribution.
So actually, I showed the slide, but I was running out of time. If you look at the dispersion measure distributions of the non-repeating CHIME FRBs and the repeating CHIME FRBs, they're pretty similar.
Wait, they are similar or they're not similar?
Well, so they differ. There's like a somewhere between a 6 and 8% probability that they come from the same distribution.
Right.
So they are the same within 2 sigma or less.
Right. So Vicky,
so the plot in the paper argued that they were different distributions, but to me that was just evidence for possibly like the host galaxy contribution from repeaters being more significant.
The width, I think you might be thinking about the width.
The TM distribution.
Microphone.
Yes, that's right.
And those are different.
Right. So okay.
Well, it's because the first one involved 12 sources.
Yeah. So that's
and the
been
second
overtaken. Is no longer. Yeah.
Well, the first one there wasn't a significant difference either.
Okay.
So Vicky, it's 2 points. One, actually, just a question. Is it easier for you to detect repeat pulses in any way? So do you, for example, have lower thresholds of particular DMs and times, or
once you found a single burst?
Yes, we have a lower threshold, but when we do statistics, if we're going to do them, we're not going to include the ones with the lower threshold.
Yep. Good. Okay.
Didn't some of the non-repeaters become repeaters, so that figure evolves with time? Because some of the ones you've marked down as non-repeaters, you just haven't got the second pulse yet.
Yeah, so we're always very careful to say apparent or as of yet non-repeaters. We don't know which is a repeater and which will not be.
What about sad trombones versus non-sad trombones?
Yeah. So Brian, back to your point as well. I think I really look forward to the volumetric rate analysis being done with hundreds of events as well. I think that would be.
I think that one thing will obviously be the host galaxy properties. If all the non-repeaters come from the same host galaxies, I might just say maybe repeaters evolve into non-repeaters or vice versa, or maybe they're fundamentally related.
So another way you could do it, we have an undergraduate student, Daniela Brightman, who's working on this, doing simulations of, say, let's say every repeater had a same Poissonian rate, and then you, which might not be true, but it has some luminosity distribution, then you spread them out in redshift space, and then you see what you observe. How many times would you see repeats? Is that consistent with what we're seeing? And if not, can you tweak anything like, they follow star formation, or they have a constant density in redshift, or maybe they just have different luminosity distributions, but they're still all Poissonian at the same rates, or maybe you have different rates, or maybe some are periodic, some are not. So the problem is that phase space to answer the question crisply using statistics is very, very large and hard, but you can get somewhere. You could at least rule out some areas eventually with good statistics.
But Vicky, 121102 is still not a repeater at Chine, is that right?
Yes.
So that's a whole can of worms that.
Yeah. Yes.
Is it a sad trombone at chime?
Alex should answer this because he wrote that paper.
I think so. It was kind of hard to say, the scattering versus the substructure. Like, it was faint and sort of unresolved. But yeah, we measured a drift rate for that.
But just once.
Yeah, just one. Yeah.
Okay. X, you want to?
What are your approaches and plans to publish analyses of your biases related to DM and scattering going forward?
That's a nice question. Survey teams want to tell us?
There's multiple teams there.
It to all of us. Why is it?
Yeah, it was all of you.
Right. Yeah.
Right.
What's our plans? Some of it was published in the 20 FRB paper. So we did some work in the supplementary material, which sort of discusses the issues with our, fat channels, etc. I think scattering is another can of worms because you need to have a model for it. But I agree that I think an interesting question is how much does understanding FRBs depend on having a good estimate of a rate, right? That's the fundamental question. Like how much, because it is hard, right? And it's kind of it could be a roadblock for some teams, right? Mm-hmm. And how much can you get by on just events?
Yeah, I think it's a huge challenge. Having 700 events as we do in Chime is wonderful, but it also means you have to do statistics. Even a simple result like just the scatter plot of DM versus scattering, say, it's easy to plot what you measure, but what's the probability that if an event had been in a particular part of that plot, you would have seen it? How do you correct for the selection is a huge problem, and that is the big obstacle that we are confronting in our catalog paper.
And I'd also turn it around and say I actually think that looking at distributions, for example, with DM, with fluence, with pulse width, and so on, are kind of hard to interpret given the lack of knowledge about a lot of intrinsic properties, like the intrinsic spectrum, like the effects of scattering in some cases on your detection biases. I think I would turn it around and sort of say, I wonder, kind of agree with you, Ryan, that it may not be the most constraining thing to have these all nailed down. Yeah, I think that's fine.
I forget which question this was related to, but I thought we should at least mention that we recognize that you certainly, if you're going to be detecting hundreds of FRBs, as we are, you'd want localizations for them. And so one thing that we are working on in parallel are outrigger telescopes for CHIME. So sort of smaller versions, but 1,000-kilometer baselines that could use CHIME as a trigger, and our trigger is already operating, but could be buffering baseband data and dump it so that you get quasi real-time localizations for those bursts, and that's something we're working on.
Cool. Harish.
Okay, so because I think you showed about 500 FRBs or something like that, right, from CHIME in the histograms. Yeah, so I think it's interesting to now think about strong lensing, because 1 in 1,000 sight lens to, let's say, redshift 1 is strong lensed, and depending on the slope of the luminosity function, you probably already have there's in a flux limited sample, there's a detection bias to lens things. So you probably already have a strong lensed source. But the problem is the typical lens is like an arc second in size, so the time delays are like weeks. So since all of you are here, I think it's nice to kind of brainstorm maybe a little bit on how you would maximize your chances of finding the second burst from the lens, like it would look like a repeat burst basically.
Daniele, did you have something?
You put on your mic?
Yeah, it's hard to hear you.
I just want to comment on that, because it depends on the lensing regime. So if you are thinking about lensing from like intervening halos, then sure, it's weeks. But if you're thinking about machos, then it could be around milliseconds. That the second part is easier to be certain, because you can use raw voltages to see if the phases of the two signals are actually coherent. In the first case, you can only do that with intensity, I think, and it's not so hard to find, two peaks that look alike, but it's much harder to find to convince yourself that these two peaks are actually the same length. How to do that, I'm not sure. If you have ideas, sure.
Liam, you want to say something?
Specifically for strong lens ring, where you do have to wait 2 or 3 weeks or months or something, and with which you can go after H0 and do cosmology and all this fun stuff. Transit telescopes could look at the NCP, so that you're always looking at the same patch, and you don't have to get lucky, for example, with CHIME, that you're just on the repeat event when the lens image shows up.
Yeah, that was my answer. The obvious thing is to build a survey which looks at either the north or the south celestial poles. So you always have the same amount of same patch of sky. This is also, of course, interesting for statistics on repeating versus not repeating. If you always have your sources always in the sky.
Yeah.
So it's interesting for many reasons.
Yeah, but then you see two bursts a week apart that look similar.
Yeah, but that's a different story. Then you go into the voltages, but first you actually have to detect the lens. And if you don't have a telescope which is constantly looking at the same part of the sky, you have to go to some sort of deeply complicated monitoring network that always tracks the source, in the hope that it eventually goes off again. Because you know maybe
where
within,
it's going to.
Yeah.
Ryan.
Do the lensed images have the same dispersion measure?
I think they should be fairly similar. If you can undo the dispersion effects and you have the voltages,
but like it's going to be like
should correlate.
But it's going to be like 50 DM units different, or 0.01 DM units different?
So this stuff is worked out, I think, in this Eichner paper from a year or two ago, and he claims that you can remove these dispersive effects and just recover the raw voltage time stream.
Yeah, I agree that. I just worry that you're not going to be able to associate them, because it's going to be 100 DM units different, and you're not going to.
I mean, as long as it's a linear filter, right? As long as it's a linear filter, you're fine. But
you might think they were different FRBs.
Yeah, that's my point.
Micro-arc second deflection angles, are you really going to get 100 units of DM difference?
Well, it depends on the time delay as well.
I think if the lensing is from a halo, the DMs can be significantly different. For micro lensing.
Yeah, I agree for compact objects. Macho techniques, it's probably fine. Modulo, you do have to undo the DM, which is not just 0.01, you have to go to 10 to the -5.
And could the scattering be different? And then you can't undo it?
But wouldn't you resolve the source if you've got a 10 kiloparsec baseline for VLBI?
Okay, let's go to Sterl, who has a question.
Yeah, I would just say staying out of the galactic plane is the obvious thing, because because rats and pulsars are mostly in the galactic plane.
Yeah. Okay. Anybody? Wenbin, did you have a comment?
Very quick comment on the strongly lensing picture. So the lensed image would arrive a week, let's say a few weeks later, and in a millisecond timescale. So CHIME is not seeing the same patch of sky because CHIME only sees an hour per day ish. So it may just miss by chance. You need actually 10 times or 30 times more bursts in order to find actually the lens one than the one over the optical depth.
But that's Laura's point about observing the celestial pole, where you're
but your area is small. If you only look at the pole, then you.
No, I mean, talking about it focuses on the pole, but you have a wide area.
It's always rotating through your telescope.
Yeah. CHIME only see a strip. Yeah. Yeah.
Pop it up.
Yes.
Okay.
I don't think any breakthrough will come from lensed FRBs in the next decade, actually. I think we should get back to talking about things that will.
Casey?
So it hasn't come up, but my favorite answer to number one is the Hail Mary, where you're looking for like supernovae or other classes of cosmological transient that are associated with FRBs. So since it hasn't come up, I feel like that is also a valid strategy for going at oddballs that are very informative.
I think it'll be very interesting to see how long repeaters repeat for. Do they last for a year or a decade, or is there going to be a conference in 1,000 years still talking about 121102? I thought it was wild how the DM's getting bigger, not smaller.
Yeah, it's pretty cool.
But I don't know what it means.
Yeah. Just on that point, though, maybe we should discuss this in a second, but is there any way that is not proper motion of the source?
But you have a flaring source, you have a shell around it. It's being, you can find the right situations where it's being ionized, slowly ionized. So you can come up with situations. You say every flare makes some ionizing radiation, which we can't observe because it's too far away, but it's sort of ionizing its way through a shell. So I think there are ways to do it, but how contrived we can describe.
Brian?
If you just sweep out material, if it doesn't change its ionization state, that will cause an increase in the DM of time under certain conditions as well.
Why does atom go down?
Isn't that just geometry? Can it just be geometry?
Protection effect.
Wait.
What's causing the RM? That's a better question.
Kiara?
I wanted to ask a question unrelated to this. So when I spent some time in Bonn, there was a person who was dedicated to advocating for keeping some radio frequencies clear in Germany to make, to help mitigate RFI. Is that still going on, and is anyone else doing this, like in a very kind of practical way of, so that you don't actually have to go in and zap so much?
People do it all the time, and we're losing because the cost of the spectrum, or the commercial cost of the spectrum, is worth all of our salaries put together many times over.
NRO has a spectrum protection officer whose job it is to try to negotiate these things. But when Motorola says it costs us 25 extra cents to put in a filter per handset, so we are not going to.
So actually, I think a transformational change we should be considering is how we can monetize the information in our band passes Because we have all the cell phone stuff. Surely there's a way to like.
That could be it.
I think we would actually have trouble getting ethics clearance for our experiments if we were dumping voltages from phone calls.
Harish?
Well, Astron did, I don't know if you can call it victory. So we have a lot of reflected RFI from windmills, and there's like, that is also a pretty big industry. And I think Astron and the company building the windmills work together to actually change some of the designs in their alternators to get rid of a lot of the RFI.
Maybe you want to use a microphone?
No, it's a
sure.
Yeah. Quick question for Vicky. What is the satellite RFI situation at Chime?
Satellite RFI. So certainly we see airplanes routinely, and that was actually figured out by an undergraduate who noticed the pattern was the same as the flight pattern out of Mexico. So I don't think we've carefully studied which of our events are satellites in Chime. I'm not sure we know the answer.
Yeah.
At Meerkat, about half the band has to be zapped in order to do FRB searching at L band.
The band.
Is that? Wow. 40 to 50%.
Yeah.
Roger, is it really? Oh, sorry. Go ahead.
Yeah, just like when we observe at lower frequency with ASCAP from like 700 megahertz up to gigahertz, it's 4G. That's the dominant thing there. So it's not the satellites. I think are typically at higher frequency.
Yeah. Okay. Yeah. All right. So we need to wrap up the discussion for lunch. So I'm sure we're going to continue this over lunch, but I do want to give the younger members of the audience before we go any chance. Does anyone want to weigh in on what kind of observations you guys think are useful or constraining, or Sriharsh?
So one of the points which was sort of tangentially made about the bright nearby bursts is that, but it was not discussed more, is that side lobes of telescopes are incredibly good at detecting bright bursts. So CHIME has probably an area of about 8,000 to 10,000 square degrees, where we can see bright bursts. But it's really hard to set up your pipeline so that you can detect them and not throw them out as bad things.
Mm-hmm.
So when you design pipelines, that's something you should consider. Like a telescope does do a very wide low sensitivity search as well.
Yeah. Excellent point. Okay, so I think we need to wrap up to go to lunch. I want to thank all of our panelists and all of the people who participated in the discussion. We've had, this has been really nice, but we have several discussions going on throughout the week, so I'm going to continue to encourage young people to speak your mind and don't be afraid to speak up throughout the next few days. We really want to hear from you. I want to hear from you. So with that, let's thank everybody and go to lunch.